don't believe in climate change. You might say, that seems crazy coming from you. I mean, you're wearing a t-shirt that says ecology on it, and I've got the long hair and all that. Don't believe in climate change because it's not something to believe in. Believe in yourself. Believe in a principle. Believe in something bigger than yourself. Believe in things that you don't have empirical information about, but yet you understand to be right or true, or for the betterment of humanity. Climate change is about inference. And inference is a conclusion or understanding that we come to based on data. In order to understand climate change and to weigh what or how much we should do about it, we need to use inference. This allows us to set aside arbitrary differences among us, such as political differences, perspectives on the world, and deal with the problems that face us. Now again, the goal here is to understand the science of this, to make inference. And I acknowledge that you have beliefs, and I think that you should embrace them while looking at the data in order to understand what it is we are confronting and what we should potentially do about it.
And what I want to do here is spend a little bit of time talking about the history of climate on Earth. This is a topic that tends to be very familiar to geologists, but less familiar to ecologists and plant biologists broadly. One of the main points that I want to relate to you is that geologists understand the Earth to have gone through some very distinct phases in terms of geologic activity, atmospheric chemistry, and overall climate. The Earth has been dynamic throughout its entire history, and some of these dynamics are shockingly wild. The Earth has been around for about, I think it's about 4 billion years, a bit longer, depending on when you want to say that the planet as we know it actually formed. Remarkably, living things emerged early on in the history of life, or the history of the Earth, you know, about 3.75 billion years ago, and have been present ever since, changing the dynamics of the Earth's atmosphere and creating the biosphere. Now, here's just a couple of crazy things that have happened in the history of climate on Earth. One is that about 2.5 billion years ago, we believe that virtually the entirety of the surface of the planet froze. We're not totally sure about why. That may have been a reaction to biological activity, but this great snowball Earth may have frozen all but the most deepest parts of the ocean. And remarkably, life persisted, and of course it resulted in a massive extinction of living things at the time. There was a second ice ball Earth that's much more recent, less than 1 billion years ago, and that's thought to be more of a slush ball Earth kind of thing, a period where the Earth was was mostly frozen, but the seas were probably slushy. There was less extinction at that time, and most of the kind of geological periods of history that you're familiar with are in the last 500 million years or so, the Paleozoic, Mesozoic, so on and so forth, until we finally get to modern day. The point here is just that. Climate has been extremely variable over the course of the Earth, and let's look at why. Why mechanistically does that happen? Well, here are a few other things that are good to keep in mind about the Earth. The physical environment is not static. I mean, especially when we look over very long periods of time, the surface of the Earth is changing. There are different periods of greater or lesser volcanic activity. These factors shape the way the planet looks, and they also influence atmospheric chemistry in ways that influence climate. And we can see this again and again as we look at the history of the planet. How variable has Earth's climate been in the past? Well, pretty variable. When we just look at, say, the period of the last 500 million years, we can see periods of time when the Earth tended to be cooler, have greater extent of ice covering the surface. We're actually in one of those periods now. The Earth is by and large on a pathway towards less ice. We've had less and less ice since the last glacial maximum, some 20 to 30 to 50,000 years ago. Now, one of the things that we see when we look across the timeline of about 500 million years is a close correlation between carbon dioxide concentrations in the atmosphere and temperatures. One thing that is probably obvious to you here is that no one was present on the planet in order to record temperature and atmospheric CO2 levels. So how do we know that that happened? Again, our goal, our task here is to understand how the Earth's climate system works based on inference, based on data. So let's look at the data. How do we know that we can trust this? Well, one characteristic of the Earth's climate system is that there are variations in what are known as stable isotopes. These are variations on familiar elements, but they have extra neutrons on them, and they are called stable because they do not experience radioactive decay. One of the most important is oxygen-18, stable isotope of oxygen. Now, oxygen usually is oxygen-16, and with 2 extra neutrons stuck on it, it's a lot heavier. What difference does that make? Well, heavier elements take more energy in order to change their temperature. So if you have water that has an oxygen-18 element in it, it takes more energy to evaporate that molecule of water. Now, oxygen-18 occurs naturally in the environment, and one of the patterns that we can see when we look across the Earth is that its concentration in rainwater decreases as one moves from the equator to the poles. There is more energy in the equator. It is more likely to evaporate a water molecule with oxygen-18, and furthermore, it is more likely to fall out of the atmosphere in precipitation closer to the equator. It just takes more energy to keep it in vapor form. Using that relationship, we can look at ice cores and recreate global average temperature based on the abundance of oxygen-18. This relationship, the depletion of oxygen-18 in precipitation changes depending on global average temperatures. We know that because we've been here recording temperature for about the last 150 years, and we can look at the ice cores to directly relate those two factors. So to say that no one was here to observe changes in temperature over the last 500 million years is true, but that doesn't matter because we understand these aspects of how the physics of the atmosphere work, and we can estimate previous atmospheric global temperature levels based on these relationships. So we weren't there, but we still know something about it. We can make inferences about how temperature has changed over the course of the history of the planet. This relationship between global temperature and the abundance of oxygen-18 is super powerful. So we don't just have the ice caps in the polar regions to tell us how temperatures have changed over these very long periods of time. We can also core ocean sediments, and we are able to examine the abundance of oxygen-18 and thereby estimate global average temperatures for longer periods of time into the past. And that's what this is showing here. These are our more recent measurements, and here we have the length of time that we've had Northern Hemisphere ice sheets, and the Antarctic ones have been around for much longer, so they have a longer record. But we can go back further in time with these measurements from ocean cores. Now, along with this, we and other isotopes of carbon, we can start to estimate changes in atmospheric concentrations of what we call greenhouse gases. We can do this both by measuring their concentration within the ice cores and by estimating the concentrations with proxy measurements from things like ocean cores. Now, like I say, we call these greenhouse gases, and that's kind of it's a fine way to describe these gases. I think the name came about in the 60s and 70s, and if we were just discovering it now, we might use a different name, but you know, it doesn't really matter. These things are so named because they absorb energy from the sun in certain wavelengths. Now, the greenhouse gases that are most important to us are not always the ones that are those that are released from pollution sources. But and really what I'm talking about there is water vapor. Water vapor is one of the most important greenhouse gases to us because having a lot of water vapor in the atmosphere actually locks in heat and makes this planet livable. What water vapor does is it absorbs energy across many different parts of the electromagnetic spectrum of electromagnetic radiation. Oxygen does too, although not as much. Things like ozone do, and then CO2, which is released by the burning of fossil fuels, also absorbs in several different wavelengths. The important thing about CO2 is that it's changing, and it can be changed through pollution. Let's set that aside for a moment and confront this problem of how do we know that these molecules absorb energy? Well, at the molecular level, there are many ways this can happen. When a photon of energy hits a CO2 molecule, many things can happen. One is going to pass through it without anything happening. It can be reflected off of it, or it can't. The energy in it can be absorbed either by stretching out the orbit of electrons or by bending the angle of those electrons, basically making these things vibrate or bounce, and that change in kinetic energy is manifested as an increase in temperature. So energy is neither created nor destroyed here. It is changing form from electromagnetic radiation to heat. And that happens in many different physical processes. Again, I want to emphasize that the second law is not violated by the atmospheric dynamics of our atmosphere. Energy, we're constantly intercepting energy from the sun, and not all of it is radiated back out into back out into space, and that's a good thing because otherwise this planet would be unlivable. So here is a depiction of changes in electromagnetic radiation that happen in the atmosphere. And this black line here is a hypothetical relationship called a perfect black body. If the Earth perfectly reflected energy at the same wavelength that it was absorbed, this is this idealized thing called a perfect black body. It doesn't actually exist. Here it is. It would the spectrum of electromagnetic radiation release from the Earth would look exactly like it does when it comes in. The Earth would act like a mirror, but that's not what happens. We have these really big discrepancies between the ideal release of electromagnetic radiation of the Earth and the actual release of electromagnetic radiation. And these big troughs, these areas where radiation is being retained as heat in the atmosphere, correspond to the absorption wavelengths of these greenhouse gases: water, oxygen, ozone, carbon dioxide, and methane. Again, the second law is not violated here. The Earth is not a perfect mirror. It's more complicated than that. The amount of energy that comes into the atmosphere is equivalent to the amount that is going in. But the spectrum of electromagnetic radiation is changed by our atmospheric chemistry. And furthermore, as our atmospheric chemistry changes throughout the history of the Earth, so does our profile of electromagnetic radiation release. So basically, what's happening here is the greenhouse gases in the atmosphere, water, CO2, and others, are holding on to some of that energy through heat. And just, again, the amount that's going in is going out. None is being created here. You can change the temperature of the Earth. And thank goodness, because if this didn't work, this would be a total, like a frozen body of rock or whatever, you know, like the Earth would be super boring and we wouldn't be here. This is essential to sustaining life on Earth, but there's a potential problem there, which is how much heat can we retain in the atmosphere? How much do we want to manipulate it as a technological society? And how much of that can we tolerate and maintain our economy and other things that we value? Okay, so there's more to the dynamics of the atmosphere than just the release of CO2 and other greenhouse gas pollutants. The volcanoes change the energetic dynamics of the Earth, and they do this in part by changing a factor that's called the albedo. And the albedo is how much energy is reflected off the surface of the Earth. This is a map of albedo. It's very low in the northern hemisphere. Any idea why? Because it's got a lot of snow on there. It's got a lot of ice. Forests have less albedo. They reflect less light because they are darker. And in fact, trees absorb electromagnetic radiation in order to power photosynthesis. The deserts of the Earth, the great deserts, have high albedo because they tend to have a light color, and that reflects a lot of electromagnetic radiation, as well as the release of compounds through volcanic eruptions also can have essentially increase the albedo of the Earth and can cool it. And this has been measured at different times, including during the historical period. The other thing that greatly affects the temperature dynamics of the Earth this is the circulation of ocean of water in the ocean. So this global conveyor, which is a pattern by which water circulates within the oceans, is very important for increasing the habitability of certain parts of the world that are in the very far in the northern hemisphere, such as Northern Europe. Northern Europe is hospitable to such relatively large populations of people because these warm ocean currents keep it warm. Once these sink and become cooler, the land masses that border those cold currents are covered in ice, or they're just very cold. I'd like to go to Labrador and Newfoundland, but I know that they are cold places and they are harder places to live than, say, London or Paris or Stockholm or something like that, even though those great European cities are much further north than Labrador and Newfoundland. Okay, and then there's other effects of this. You can see these effects in other places on the surface of the Earth that are warmer or cooler than we expect, and that is a direct effect of these ocean currents. Okay, so let's get to the meat of all this, and the part that bizarrely is controversial, and that's greenhouse gases that are released into the atmosphere through fossil fuel burning. What we can say, because we've measured it directly, is that concentrations of greenhouse gases, particularly carbon dioxide and methane, are increasing steadily over the last several decades. And furthermore, what you can see here is the effect of the global forests on influencing those CO2 dynamics within years. You can see that it's higher in the winter and lower in the summer, the northern hemisphere winter and likewise the northern hemisphere summer, because these forests are absorbing that CO2. The other thing that's very clear from this is that these overall concentration levels, are steadily marching upwards over time, and these are tightly coupled with the amount of fossil fuel burning that is currently driving our economic systems. Now, again, I'm not here, and I don't even believe that burning of fossil fuels is wrong. I'm not here to convince you of that. Our job here is to understand what the data are telling us so that we can make some informed decisions about what we may or may not do about this. I do not have the answers in terms of the solutions here, but the data leads me to be very confident in the inference that atmospheric greenhouse gases are increasing due to economic activity, and furthermore, that those will have consequences in terms of changes in atmospheric temperature. What you think should be done about it, whether or not you think anything should be done about it, is something we can talk about. Like I say, I don't have the answer, and I don't think anybody does. But the first thing we have to do is acknowledge those things that we can make strong inferences about, and this is one of them. Now, unfortunately, there's a lot of misconceptions, intentional or otherwise, that kind of run wild about about global warming and climate change. And I think it's tragic because we can't act on it to do things that might be sensible unless we're all sort of on the same page. I always like to point out that a good conspiracy theory always has an element of truth or plausibility. So, for example, let's just go through some of this stuff. Is the Earth's climate variable through its history? Yes. Yes, it is. The current changes are more rapid than any on record, and they are following the usual pattern of increased greenhouse gas concentrations. Furthermore, we can trace those greenhouse gases back to the burning of fossil fuels. So there's evidence here. We can make a very defensible inference that economic activity of our modern society is changing the climate. Whether you think that that's worthy of action or not, we could talk about again. Here's another one that I think is that I always like to point out. Climate change cannot occur because it violates the second law of thermodynamics. Well, I think that's a selective application of facts. Climate variability does not violate the second law, because we're not creating or destroying energy, we're just changing form from electromagnetic radiation to heat. And furthermore, the amount of energy that comes into the Earth system is equal to that goes out. The second law is not violated by the idea of climate change, nor of economic activity influencing it. And here's just one last one. Forecast changes in temperature are much lower than diurnal variation. This is just wildly misleading to the point of just seems like deliberate misinformation, if you will. 1 degree of temperature or 5 is not much than the difference between the difference in temperature from one day to the other. We are not talking about that. We are not talking about diurnal variation in temperature when we discuss overall changes in temperature. For that matter, those things are, sure, yeah, you're comparing temperature, but you're not comparing it in a way that it is at all can be equated. 1 degree change in the overall temperature of the Earth, the average temperature of the Earth, has a much greater influence than just simply saying that one day was kind of cooler and one day was hotter. The implications are much bigger. The other one that I love is that without greenhouse gases, life would not exist on Earth, and that's completely true. Mars lost its oceans. At one point was covered in water when it lost its oceans, and it lost most of its atmosphere with that, and now it's mostly a frozen body. Yeah, True, but we're not at risk of losing our atmosphere here. What we're doing is changing it. And so, again, I'll say this again. My job here is not to convince you that one policy change or another is correct. I don't know what the policy answers are. This is a hard problem, and that's why it's never been really tackled. But we're never going to get anywhere with that unless we acknowledge how our biophysical system works. And once we do that, and we all kind of have a shared vision, a shared understanding of reality, then we can talk about what we might do, whether it's worth it, and how we might affect that. And that just seems like a much more solid place for society to stand. And I hope that at least you will think about the difference between inference and belief as you look at this kind of scientific data and ask, what is it that we might do in the future that's different in order to protect our economic systems or our society?